When we design systems to process the behavior of the global internet, we build structures stretching into millions of rows and billions of columns. This diagram represents a utility matrix. It is the core architectural tool for tracking relationships, plotting millions of users on one axis against billions of items on the other, mapping every web click, movie rating, or e-commerce purchase. But looking at the whole structure reveals a defining physical characteristic. 99.9. The standard mathematical method for this compression is singular value decomposition, or SVD. It takes the messy data and perfectly isolates the hidden concepts driving user behavior. But running exact SVD on hyperscale data introduces a fatal flaw. The math is theoretically perfect, but applying it to a sparse matrix destroys the sparsity. When the algorithms fill the zeros with actual values, the sudden demand for physical memory crashes the entire system. To process data at a global scale, engineers must abandon exact mathematical certainty. They survive the physical limits of hardware by using a probabilistic sampling method called CUR decomposition. This diagram shows a heavily simplified, dense utility matrix. We have 7 users in the rows and 5 movies in the columns. Woven into this data are 2 underlying genres, science fiction in blue and romance in red. SVD factors this original matrix, called M, into the product of 3 component matrices, U, sigma, and V transpose. The U matrix maps our original rows to newly discovered latent concepts. It scores each user's exact affinity for science fiction or romance, stripping away the individual movie titles. The V transpose matrix does the inverse. It connects the original columns, the movies, to those exact same latent concepts. Sitting between them is the sigma matrix. It consists entirely of zeros except for a diagonal line of numbers. These are the singular values, and they dictate the mathematical weight or strength of each discovered concept based on how much data supports it. For the equation to remain perfectly balanced, SVD enforces a strict geometric constraint. The columns of U and the rows of V must be orthonormal. They operate as independent unit vectors, completely distinct from one another. By factoring the matrix into these components, SVD isolates the latent affinities that dictate why a user chooses one item over another. Looking at the sigma matrix allows us to actually compress the data. We reduce the dimensions by targeting the weakest concept, the lowest singular value on the diagonal. When that lowest value is forced to 0, any numbers multiplying against it become mathematically irrelevant. We can physically slice off the corresponding column in U and the bottom row of V transpose. The matrices shrink. Dropping the lowest singular values provides the strictly optimal low-rank approximation of the data. It minimizes the root mean square error between our compressed model and the original massive dataset. Here is a new one-dimensional vector, representing a new user named Quincy, who has only rated one movie. To generate recommendations, we query the compressed model. Multiplying Quincy's raw ratings by the V matrix translates him out of movie space and directly into concept space. We now have a clean 2-value vector showing his exact affinity for the underlying genres.
Dimensionality reduction saves hard drive space, but its utility goes further. It maps noisy, fragmented user behavior into a clean, universally comparable coordinate system. But we have to return this mathematical model to the scale of the real internet. Here is our hyperscale matrix, defined almost entirely by empty space and zeros. When we factorize this sparse dataset with SVD, the exactness of the math forces the data to become dense. The resulting U and V matrices fill up with highly specific floating point numbers. The algorithm requires orthonormal eigenvectors to maintain perfect accuracy. Eigenvectors do not inherently preserve zeros. Storing an empty cell in a sparse matrix costs almost nothing. Storing dense floating point numbers across a grid of millions by billions requires intractable, exponential amounts of RAM. The physical hardware fails under the weight of perfect mathematics. Memory limits are breached, and the processing clusters crash. Pure algebra assumes infinite memory. Data engineers have to pay for physical servers. The exactness of SVD is physically fatal for massive data. To stop the memory overflows, engineers use an alternative called CUR decomposition. This method completely abandons the requirement for exact orthogonal vectors. This diagram shows the CUR layout. Instead of calculating brand new, highly dense matrices, CUR physically samples and builds its model by extracting existing columns and rows directly from the original sparse dataset. To build the C matrix, the columns, the algorithm must decide which vertical slices of data to pull. The selection is randomized, but it is heavily weighted to favor the most important data. The system calculates the squared Frobenius norm, the sum of the squares in a single column. Dense columns score high, empty ones score low. The highest scoring vertical slices are extracted and stacked to form the C matrix. To prevent distortion, chosen columns undergo a scaling phase, dividing values by the square root of their selection probability. This exact sampling and scaling is repeated horizontally, extracting high-density rows to form the R matrix. Because C and R are raw slices of the original data, they inherit its exact sparsity. The zeros are preserved, bypassing the memory overflow entirely. Here is the empty space for the U matrix. To connect our sparse columns and rows, we locate where they cross within the original matrix. Those exact intersection points are extracted to form a small square matrix called W. The algorithm requires the inverse of W. Because W is sparse, it's rarely perfectly invertible. The solution is the Moore-Penrose pseudo-inverse, running SVD on W and inverting only the non-zero elements. This transformed matrix slides into place as U. The U matrix is the probabilistic bridge. It mathematically scales and aligns the raw, disconnected sparse slices into a unified approximation of the entire dataset. This split screen shows the final structural difference. On the left is SVD, perfectly interlocked, but requiring massive, dense blocks of memory. On the right is CUR, an approximation built of lightweight, highly sparse blocks. CUR decomposition forces a mathematical concession. Because it restricts itself to sampling existing data, it cannot guarantee the exact minimal error rate that SVD achieves, but it guarantees sparsity. When tracking billions of inputs, preserving empty space is the only physical way to keep the matrix alive in production hardware. SVD remains the theoretical ideal for understanding latent structures on smaller datasets. CUR is the operational reality that allows dimensional reduction to exist at all. QRU proves that strategic, probabilistic approximation is the necessary compromise for making high-dimensional data computable at global scale.